let me skip the spring. We are running out of time, and I don't think spring is important to you guys. If you're interested, there's things in the textbook you can watch, you can look. But now we are going to do things in a slightly different approach. In the previous section, we used work and kinetic energy. But we all know we begin with something called potential energy. So what exactly is potential energy? If you look at a piece of leaf and it flies blah 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 blah, it flies down. You guys see the leaf? Okay, good. So when a leaf flies down, we can analyze this process with work kinetic energy theorem. The work done by gravity will be gravity divided with its displacement. Now, gravity is always going down. So when you look at the displacement of this leaf, the x displacement doesn't matter. The dot product will pick up the component along the direction of gravity. So the only component that matters is the change of y. So you get the magnitude of gravity times the y displacement. So y displacement is going to be, let me say negative delta y, because I'm going to say delta y is negative. And because they are in the same direction, we know the work must be positive. So this gives me a positive work done by the gravity. It's kind of weird because now the displacement has some delta x. It's negative, good, and some delta y. But I want to use y as the height of the so maybe let's just call it h, okay? So h is this height difference. Then we have the displacement is going down by h. That is easier for you guys to see. This is negative gravity times negative h, which is positive. Gravity has a negative y component, same as the displacement, so you get a positive work. Gravity pulling the leaf down is doing positive work to the leaf, so it increases the kinetic energy of the leaf. But if you see I draw the trajectory like this, you know there's air friction. Air friction is constantly changing its direction. So if you want to calculate the work done by air resistance, it's going to be hard, and I'm not going to do that. You don't need to know how to do that. But you do know WF stands for the work done by air resistance. And because when it moves right, air resistance will be pointing to the left, the work done by air resistance should be positive or negative? Yes, we don't know how big exactly, but it should be negative. Air resistance is decreasing the kinetic energy of the leaf. So totally, the work done on the leaf will be work done by gravity plus the work done by air resistance, and that will equal to the change of the kinetic energy of the leaf. We don't know how to compute the work done by air resistance, so that's just why that is. But the work done by gravity is easy. You don't even need to know what the path looks like. It only depends on the initial height and final height. It only depends on how much has the height of the leaf changed. The work done by gravity is easy to compute. So it is convenient to think of the work done by gravity as a change of potential energy. There's a minus sign because what I'm going to do is to separate the work done by gravity from the work done by friction. To do that, I move it to the other side and get the work done by friction will equal to the change of kinetic energy minus the work done by gravity. Okay? I'm moving it to the other side because these two are very different. This is very easy to compute. It only depends on the initial and final height. This is hard. They are very different. So I move it to the other side and call this work with a minus sign as change of potential energy. The minus sign comes from moving the work to the other side. Okay? So we get the work done by friction will be the change of kinetic energy plus gravitational potential energy. I use G because it's caused by gravity. And now we see if there's no air resistance, the sum of energy is a constant. We get energy conservation. So energy conservation is just another way to view work kinetic energy theorem. When there are some force that is easy to compute their work, we say it's a conservative force. And this is the work done by conservative force. Conservative force is just something that is doing work which is easy to compute. The work done by conservative force is easy. In this case, it's just the initial height minus the final height. For other force, like air friction, air resistance, the work done by those non-conservative force is just the work done by non-conservative force. It's hard to compute. It depends, for this case, the air resistance, it depends on exactly how this path looks like. It depends on the shape of the leaf. It depends on a lot of things. But this is just two numbers multiplying together. And in this case, because the change of gravitational potential energy is defined as the work done by gravity with the minus sign, you see we get a minus FG H. H will be, so the gravity is mass of the leaves times G. Gravity is just mg. H will be minus the height difference. Now this delta y means the height difference, not the difference between initial and final state. Delta y is going up. Okay? The y position of the leaf goes from higher to lower. So delta y here is a negative number. That's why h here is a negative delta y. and then you see the minus sign cancels, and then change of gravity will just be the change of gravitational potential energy is just mg times the change of height. If your y position goes higher, your gravitational potential energy will also go higher, which makes sense, like what we start with. Okay? So when you go lower, your delta y is negative, your y position is decreasing, so your potential energy is decreasing. But because the work done by gravity and the change of potential energy have a minus sign, so the work done by gravity is positive. So there are two ways to view this problem. One is that gravity do positive work to increase the kinetic energy of the leaf. Or we can say the work done by gravity with the minus sign is the change of gravitational potential energy. So when the height of the leaf decreases, the gravitational potential energy decreases, and that goes into kinetic energy. There are just two different ways to describe the same thing. The only thing you need to be careful is you do not double count the work done by gravity. We say either the work done by gravity plus the work done by air resistance is a change of kinetic energy, or just the work done by air resistance will change the total energy. We do not say work done by friction plus the work done by gravity will change your total energy. This is not true because you are double counting gravity. You either say gravity do work and that change kinetic energy, or you call the work done by gravity as some kind of energy, then say the other work will change energy. You do not double count the work done by gravity. Okay? The total work will change kinetic energy, not energy. If you are using potential energy, then you need to not take the work done by gravity into account, because you have already taken the work done by gravity into account by writing it as a potential energy. All right?